Okay, copper 2 chloride is Cu plus 2. Chloride is minus 1.
You said chloride? I thought you said fluoride.
I said chloride. So we're going to put them together to get a formula of what? CuCl2. CuCl2, right? We can either see that we're going to need another chloride, or we can do our crisscross method, okay, which means we would ignore the plus and the minus and bring those down as subscript, CuCl2. Okay? All right, okay, give me the breakdown of binary ionic compound. Okay, it's balanced. Okay, I guess I would agree with that, yes. Give me more specifics. It's between what two things? Cations and anions, I would agree. My handwriting's a disaster because my Apple Pencil's not working, but okay. Binary ionic compounds. Okay, so they have a cation and an anion. So number one thing about it is that it's a plus and a minus that go together. In what order do they have to go together? Which one has to come first? Cation has to come first. So it would be cation, then anion. What does it mean to be binary? How many different elements are we going to have? Okay, so binary means it's between two elements. That won't always be the case, but this is what we start with. Okay, we can build more complicated ionic compounds in a little bit, but we started with binary, which means between two. And then, Michael, what did you say it has to be? Must be balanced. Okay, and so what that means is that our charges for each of those cations and anions have to have a sum of what? What's the sum of those charges need to be equal to? 0. We want it to be balanced, so neutral. We need it to be 0. Okay? Tell me a little bit about the naming part of it. The cation gets to do what with its name? Keep it. Yep, the cation keeps its name. And what does the anion do? Good. It ends in IDE. So IDE. And that's exactly what your periodic table of ions says, right? It does that for you. All of these anions here are already listed as IDE because they have the charge with them, right? On the neutral side of your periodic table, where everything is neutral, they have their regular ending. But on the charge side, or the ions side, we have an ending of IDE. Okay, so let's do a little bit of review here. Give me the chemical formula for, let's try a couple of these. Give me the chemical formula for rubidium nitride. Okay, I give you the written name, you give me the chemical formula. So these are just extra from your notes pages. They can be done in the margins or other notes, whatever you want to do. Rubidium is in group 1. Okay, rubidium's in group 1. Do you need to get your notes and stuff?
Yeah, I'm sorry.
Okay, go do that quickly, please. Rubidium nitride. First thing we do is write them out as charges. And then what's our method for getting them to fit together? Remember what that's called? What do we call that? The crisscross method. We can use the crisscross method if we want. So rubidium is RB. I know it has a +1 charge. And nitride is just N -3. So can you see right away, do those fit together automatically? Do they fit together 1 to 1? No, it's a little bit easier to see the charge because this one's a 1. So we automatically know that we need 3 rubidiums. But if we can't remember that, we ignore the plus and the minus. We bring them down as a crisscross and we get RB3N. Do I need to write the 1 right there? I don't, right? If it's a 1, we assume it can be left off, right? We assume a 1 there unless there is something else listed. Okay? All right, very good. Try this next one for me. Try Zirconium oxide. Zirconium oxide. Try that one for me. To try a couple here on your own. I'm going to give you the formula now, and you're going to give me the written name. Okay, I'm going to give you that formula. You give me the written name. You have to decide, does it need a Roman numeral or not? Right? If I'm using calcium, I don't need a Roman numeral because it's not multiple charges. But if tin, SN is tin, it's in group 4. Okay, tin is in group 4. If it has a multiple charge option, that means you must include a Roman numeral. Maybe? That's okay. Okay. Tell me without the Roman numeral. What would it be without the Roman numeral? Tin what? Tin oxide. All right, who feels confident in the Roman numeral they chose? All right, Claire, what do you think?
4.
Tin 4 oxide. Good. Anybody have tin 2 oxide? Okay, no, what's your question?
Can they cancel or you just...
Yeah, okay, so this is a really good question. How do I know that it's tin with a +4 charge? Walk me through that. Yeah.
But also, like, how do you know when to do the crisscross, or how do you know when they're going to cancel?
Okay, so here's what happened here. Tin, we assume there's one of them. Oxide, we assume there's 2. So if we reverse the crisscross and we bring this up and this up, that would leave us with SN plus 2 and O minus 1. Is that oxide's normal negative charge? It's not. Oxide's normally minus 2. And so you've got to realize if this is supposed to be minus 2, then this must be plus 4. Okay. The other way you could think about it, which tends to make more sense to me, is that I know that the oxide charge never changes. So if I have 2 oxides that are each minus 2, that means over here I have a total of minus 4, and I only have 1 tin atom to take up all of that, so it would have to be plus 4. Okay, so you can think about it either way. You can either try to reverse the crisscross method and see, is that the anion's normal charge, right? SN plus 2, O minus 1. Or you can just look at what is the charge and how many atoms are there to be able to cancel it. But yes, we should have had tin 4 oxide. Okay, let's try another one. Give me the written formula for this. Fe3P2. Give me the written formula.
Fe3P negative 2? Okay.
Do I need a Roman numeral? What do you got, Brad?
I've got Ca2N3.
No, just give me the written name, right? This is our formula right here. So what would our written name?
Calcium 2 nitrate.
Calcium nitride. But do we need the Roman numeral? Nope, so we don't write it or say it, right? Because calcium only has one option on its charge. So we don't write the Roman numeral if we don't need it. Okay? Okay, let's ramp it up a little bit. We're going to go pay attention at this box right here in the middle. Okay? The top of that box says table of polyatomic ions. So what does polyatomic mean? Many or multiple atoms. Okay, so these are ions, which is a charged particle that is made up of multiple atoms. Okay, polyatomic ions. I'm going to give you a list of about 10 of these out of this box that we're going to memorize because we use them a lot and it will speed up your process, okay? But polyatomic ions are really simple to name because they don't have to change anything about themselves. They get to keep the name that's given to them up here in the box, okay? So take a look at the polyatomic ions. What are their charges? Are they mostly anions or mostly cations? They're mostly anions, okay? So these guys will get to keep their name, Okay, it will always be named, if you're going to use, let's say, let's look in the middle, one towards the bottom. If you're going to use nitrate, nitrate is NO3 with a -1 charge. It just keeps its name nitrate, right? You don't have to change it to IDE because we need to look at some differences here, okay? I want to show you a pattern that you're going to see. Okay, I'm going to show you a pattern with these polyatomic ions, okay? NO3 -1 is called nitrate, okay? NO2 -1 is called nitrite. Nitrate and nitrite. Okay, that's one pattern I want you to see. I'm gonna put up another one. You don't necessarily have to write these down, but I want you to see it. PO4 -3 is called phosphate, and PO3 -3 is called phosphite. Do you see a pattern developing there? What's the pattern between 8 and ite? Okay, it does have more, but let's look at the pattern more specifically. This, to go from 8 to ite, means we lose 1 oxygen. Okay, it doesn't matter how many oxygens we start with. Nitrate is NO3, but nitrite is NO2. Phosphate is PO4, but phosphite is PO3. Okay, so let me put another one up here. If sulfate is SO4, what would sulfite be?
SO3.
SO3, and what would the charge be?
SO2.
Still -2. The charge does not change. So when we start looking at these polyatomic ions and memorizing them, we're only going to memorize the 8s. Because if we know the 8 version of it, we automatically know the ite version of it as well, because it's just 1 less oxygen. Does that kind of make sense? Yeah. Okay. And then what if I had sulfide? What would that be? Just regular S-2, right? It's no oxygen attached. So that is not a polyatomic ion. That's just an anion. Right? That's not a polyatomic ion. But we need to understand the difference, because in naming, we have these really small distinctions between different compounds that make a big difference in how the compound reacts and behaves and stuff like that. Yeah?
What is SO2?
SO2 -2 would be called hyposulfate. It's another distinction. And then if you add 1 on top of an 8, it's called a persulfate. But I'm not going to make you extend the pattern anymore. But yeah, that would be another one. But we're going to go with these two. So if we know the 8s, we automatically know the ites. Okay? So let's practice some naming, and then we're going to do a little group work with these. So let's see here. I'm going to clear this, or give me some room here. Okay, what if I have this formula, or this lead 3 sulfate. Lead 3 sulfate. Let's figure out what is the chemical formula for lead 3 sulfate. First, you got to find where lead is. Do you know what lead's atomic symbol? It's Pb, right? And it's in group 4. Okay, lead 3. Okay, you see how lead 3 is not listed? Yeah, that's okay. Okay, the ones that are listed here are the most common. Okay, the most common, but they could have more variations. Just trust what your Roman numeral tells you. Okay, so this would be lead plus 3. Sulfate, we're going to find in the box, and in the box they're listed alphabetically. Okay, sulfate. So what is sulfate? It is SO4 -2. Okay. They list their charges as 2-, and I say -2. It means exactly the same thing. Okay, it doesn't make a difference. Okay, so how am I going to put these together? Any thoughts? Let's crisscross. So we're going to bring that down, PbSO4 3, like that.
Do you multiply that?
Okay, so here's what we need to do. Can we just change this to make it a 3? No, we can't do that, right? The biggest part of being a polyatomic ion is this is its identity. We don't ever change that 4. That 4 as a part of sulfate is non-reducible, okay? at all. We don't change its identity. Sulfate is SO4, so non-reducible. But if I need to have a 3 on the outside of that, I'm going to put parentheses around there to show that I need 3 of these sulfate molecules. Does that kind of make sense? So if you ever need more than one of a polyatomic ion, you put the parentheses. So you might want to make a little note of that, okay? The rule is if you need more than one of a polyatomic ion, add parentheses. Okay, can you figure out what that shorthand says? If you need more than one of a polyatomic ion, you have to add parentheses around that. Okay, and so what this tells us is that we have 3 SO4s. And if I was going to look at individual elements, how many sulfur atoms would I have here? 3, because I have 3 times 1. And how many individual oxygen atoms would I have? 12, right? Because I have 4 per molecule, and I have 3 molecules, so 4 times 3. We're going to multiply those together. Okay, and last thing I want to look at here is this reducible in any way? Can it be reduced at all? No, because really I'm looking at the 2 and the 3, and that's not reducible because I don't get to touch the 4 in sulfate. Okay, how are we feeling about that? Love it? The good news about polyatomic ions is that they just get to keep their name, right? We don't have to adjust anything there. Okay, let's try one here. Let's try nickel 2 hydroxide. Nickel 2 hydroxide. Nickel 2 hydroxide. Hydroxide is in the box, right? It's not just a regular element, so it's going to be found in the box.
You need your parentheses. There you go.
Good job.
You're a good little boy, Texans.
If it's a negative charge, we like polyatomic, we don't have to put negative, do we? -1, or just negative.
You don't have to put the 1, I don't care. Okay, is that it right there? No, this doesn't work because I don't just need 2 hydrogens, I need 2 of the OHs, so I have to include parentheses.
Yeah.
I have to include parentheses. So hydroxide, it's okay, hydroxide is one that's really tricky in that way, and it'll be one that we forget a lot, but we have to include parentheses because if we don't, we're saying we need 2 hydrogens but only 1 oxygen, and that's not the case, right? We need 2 hydroxides, and so we have to make sure that we include parentheses there. Okay? All right, I'm going to try one more here, and then we're going to do a little group work. So you're going to give me the written name of this one. Okay, let's see what we got. Did I write it incorrectly? Can I reduce these 3s? I can't, right? This 3 is part of the identity of that polyatomic ion, so I don't change that. Okay? All right, what should it be? Cobalt what? Cobalt,
3.
not 2. Cobalt 3. Then what? Sulfite, because it's SO3. Okay, so let's figure out how we knew that, right? I'm going to either reverse the crisscross. That leaves me with CO plus 3, SO3 minus 2. I can look at the anion there and say, yep, that's what it's supposed to be, which means the plus 3 checks out. Okay. Cobalt 3 sulfite.
On our polyatomic.
First category that we're closing up here is ionic compounds, right? That's the first thing that we're closing on. So ionic compounds are between what two things? Anion and a cation. That's what we've been doing, right? Or metal and non-metal. But we've just finished this first category of naming, and it's ionic compounds. Metal, non-metal, or cation, anion. The next one we are moving to, I think, is much simpler. These are called covalent compounds. These are formed between two non-metals. Two non-metals. So look on your periodic table here and figure out typically what's the charge of a non-metal. Is it positive or negative? Negative. Nope, negative. Non-metals are over here. Right? Non-metals are to the right of that stair step. Okay? So non-metals are both negatives. So let me ask you this. If I'm trying to put together two negative charged ions, will I ever be able to have a neutral compound? No. So in covalent compounds, we ignore the charges. Okay, we ignore the charges. We do not have to concern ourselves with the charge of our compound. Okay, because I'm putting together two negatives. And so the reason these work is because we're not trading electrons anymore, we're sharing them. And so the way that a covalent compound fits together is different than the way an ionic compound fits together. Okay, but that's what you need to remember about covalent compounds. They have charges that we don't care about. Okay? In covalent compounds, we are going to use what are called prefixes. And the prefixes are things like mono, di, tri, tetra, right? We have a whole list of 10 prefixes. I think those are going to be in your book here in a second. If not, I'll put the table up here on the board, okay? But we're going to use prefixes. I'm going to give you an example and see if we can come up with some patterns for naming covalent compounds. Let's look at these, okay? I have two covalent compounds here, CO and CO2. Okay, what are the names of those formulas? You might know these. What's this one for sure? Carbon dioxide. And anyone know what the name of this one is? Carbon monoxide. Okay, so I want you to see what are some patterns we see here with how these are named. They have a prefix. Now, which element gets a prefix? The second element gets a prefix no matter what. Okay, that's one of the rules we have marked up here. The second element always gets a prefix. Second element always gets a prefix. Okay? The second element ends in I-D-E. So it ends as if it's an anion. But the first element uses its full name, right? You'll notice it's not carbide dioxide. It's carbon dioxide. So it keeps its regular name. Okay, so there's rule one. First element keeps its regular full element name. Second element ends in IDE. Second element gets a prefix no matter what. But it says the first element only gets a prefix if there is more than one of that element. So we don't call it monocarbon monoxide, right? We don't name it like that. We would just name it carbon monoxide. Okay, so there's the 4 rules that we have to fit in that apply to every covalent naming. Now, with covalent compounds, there is no crisscross. No, nothing. We're just name it exactly as we see it. So it's much simpler than ionic naming. Okay, much simpler. So let's try this one. Let me find you the table here. We usually think of 4 being quad, right? But here we're going to use it at tetra for 4. The other ones I feel like are all ones you've seen before. Would we agree with that? Penta
never mind, just kidding.
means 5. Yeah, like a pentathlon or something. I mean, you might have
I
seen
had
those
to think
before.
about geometry for a second. I was like,
Yep, a pentagon, right?
You want to-
Okay. All right, so there's our prefixes. Let's just try a couple here. These are simple. Okay, so what if I have this? N2O3. What would I call it? No crisscross. I just name it exactly as is. So I would call it dinitrogen. It keeps its regular ending. Dinitrogen trioxide. Trioxide. Second one gets an IDE. Okay, dinitrogen trioxide. We always name our compounds. Listen, we always name our compounds from left to right on the periodic table. So if you get a compound between two nonmetals left to right, if they happen to be in the same group, you name them from bottom to top. Okay, so you name them bottom up. So what if we had this? PCl3. Almost. No. It's just phosphorus. Remember, the first one only gets a prefix if there's more than one. That's a tricky one. That's okay. So phosphorus trichloride. Trichloride. Okay, there's one more kind of rule here that I want to introduce as more of a speech and a spelling rule. But take a look again at C, just CO. We called it carbon monoxide. Here's what we did not call it. We did not call it carbon monoxide. Okay? So the rule is if our element begins with a vowel, okay, if our element begins with a vowel, we drop the O or A from the prefix. Yeah, so that one you would get to keep it. If it was like I3, you would call it triiodide. I don't really know why. Okay, but if you had with tri, it always gets to stay. It's the O or the A that gets dropped. So if we had if we had O4, right? Let's just say we had one like this, S2O4. I would call this disulfur tetroxide, not tetraoxide. Okay, it's not a huge deal, but it's more of like the way that we speak these compounds. So disulfur tetroxide. Okay, so if our element begins with a vowel, we drop the O or the A from the prefix. And remember, no crisscross here. We name it exactly as we see. Exactly as we see. Okay, so what if I gave you this one? If I said tricarbon pentachloride. Tricarbon pentachloride. Give me the formula for it. What would it be? C3Cl5. Penta is 5. Sorry, you can't see that up there. C3Cl5. Okay, simple, right?